Hi, we're Project Slammr, which stands for Simultaneous Localization and Mapping Mobile Rover. I'm Jason, this is Brian, and that's Chenny over there. Space. And I'll hand it off to Brian.
Okay, so the focus of our project is mobile robotics. So unlike traditional stationary robotics, mobile robotics is a fairly bleeding edge field and has fairly useful applications in disaster response robots, maintenance robots for different buildings, and our high-level project goal for this is to develop a sensor-rich mobile autonomous platform. And next slide. So the software we're using for our project is we're operating on Ubuntu 12.04, which is the latest officially supported version of Ubuntu, and it's pretty easy to code on and pretty easy to navigate UI, so that's why we chose it. And next slide. For the robot itself, we are running Robot Operating System, which is also called ROS. So unlike a traditional OS, the ROS runs on a publisher-subscriber model. So in that sense, it has software modules called nodes that will, instead of outputting data, it will send this data as a sort of publishing this data to a certain topic. And then other nodes can also subscribe to that topic and then take data from that topic. So this is an asynchronous way of transmitting data. And there's also something called a service, and that's the way that you can synchronously get this data. Some key features of ROS that we really liked. Next slide. Yeah. Some key features of ROS that we really liked was that it was tool-based. So there's two tools we heavily use called RViz and Gazebo. RViz allowed us to visually look at the different topics and see the data that was being outputted, and Gazebo allowed us to simulate a robot in an environment that we created in the simulator. ROS is also decentralized, multilingual, thin, and free and open source, which we really liked. And I'll hand it over to Jason.
All right, so I'll go over a quick hardware overview. So this is our Slammr platform, which has 4 main components and the mounting plates. So as you all know, this is the platform that we use in the class lab, and it's the one we use for our Slammr platform. And this iRobot Create was a hobbyist robot designed explicitly for robotics development. And it integrates into ROS using an open source package that is thin and therefore independent from ROS. So the code that we created for this project could be used for another platform as long as it has another thin driver. And the 2 important parts of this iRobot Create are the wheel encoders that we have on the robot, which is a little inaccurate, so I'll talk more about that later. And front bump sensors, which we programmed in our forward navigation to make sure it stops in cases of collision. And the next hardware of interest is the Kinect right there. And Kinect was developed by Microsoft for the Xbox 360 gaming console, but now has popular use in computer vision systems. And it has 1 IR emitter and 2 IR sensors, which basically project the depth map onto the field, which in data is actually a point cloud data. That point cloud data is converted into 2D laser scan data in ROS, which allows us to do various algorithmic operations on it. And this Kinect is also equipped with the optical RGB camera, as is standard, and it connects to this system via USB. And one important thing about the Kinect is 1 USB cable is actually not enough to completely power the Kinect. So we actually have a power board connected to the serial port of the iRobot Create. So as you can see here, this is the 12-volt output to the Kinect. Make sure it's powered, and that basically siphons the battery power from the iRobot Create. And we also have a 3 degrees of freedom yaw gyroscope there. And how we use that gyroscope is we use it to calibrate the wheel encoders using linear regression and I believe least squares. And sadly, the most important part of it all is this gigantic laptop on top of a robot. We originally wanted to shoot for a netbook that we could put into this docking bay right here underneath, but we made do with what we had. And a typical coding environment is we would have this master laptop placed upon this Turtlebot platform, and we would have other ROS workstations running Ubuntu. And all these laptops would connect to one private network, so they all have a statically assigned IP. And communication over the ROS clients, I should say, happens over TCP/IP. And one important thing that I like to reiterate is something Brian brought up, is that ROS is decentralized, which means all the code and algorithm that we run for this project is running on this computer. It's not running on a remote computer sending the commands. It's actually running locally on the robot. So now, on to the technical challenges. So first of all, none of us really knew how to use Ubuntu. That was really hard for us. But using online resources, we kind of got the hang. We kind of just took it and ran. And ROS was likewise. We had to use a lot of online resources and a lot of tiers, actually. But the most important and the most devastating problem we ran into during this project was the networking difficulties. So we tried tackling this problem in multiple ways. First of all was using airbears and creating a VPN network using Hamachi. That was not reliable because airbears would dip in performance randomly, and we could not maintain a stable connection. So we decided to buy our own private router, as you can see in the middle there. It's a portable travel router. It failed on us 3 days ago. No reason. And now we couldn't connect. So we just bought another home router, and that works really well, thankfully. And hopefully that will be the end to our networking problems. And now the last challenge isn't much of a technical challenge, but I felt like it was pretty real for us anyway, so I put it in there. And time management. So we didn't know how fast the batteries would discharge, how fast the batteries would recharge, how fast our algorithms would discharge the battery, and how long it would take to implement those algorithms. And just balancing that was a bit of a circus act for us. But we feel like having to write the milestone reports for the project as we went on really helped in staying on track with all the stuff that we want to achieve. And I'll hand it over to Chen Yu.
So I'll be talking about the SLAM algorithm that we implement on Turtlebot. So basically, the SLAM indicates simultaneously localization and mapping. So it's a scheme that you put a robot in an indoor environment, and you let the robot know where it is and trying to map out the rooms for itself. So there are basically two kinds of SLAMs that we implement on Turtlebot. The first one is G-mapping. G-mapping stands for grid mapping. So basically, it's just stitching all the scans that it collects from the laser scanner or the Kinect sensor that we have from the point cloud information, and it stitches all the scans that it have to build up the map. So this is the map of Corey 204 that we built up. And you could tell that this is the entrance, and this is where the people generally works on. And it's nothing the same like the room that we currently have because people are crowded. But so that's the first kind of SLAM that we implement on Turtlebot. And the second kind of SLAM is RGBD SLAM. So RGBD SLAM is is a little bit different from the scan stitching one. So remember, when you're collecting all the scan data, it tends to have too much information to be collected. So this kind of SLAM is collecting just feature of the scan that you have. It's collecting the RGBD, which is the color feature, and also some like straight corner of the scan. So it uses only those features to localize itself rather than stitching all the scan data that it has. So these are the two SLAMs that we implement on our project Slammr. And because of we're achieving the waypoint navigation in our project goal, so we will need a more accurate grid map of the room. So that's why we use the first SLAM, which is the scan stitching one, to accomplish the waypoint navigation. So we're using adaptive Monte Carlo localization, which is essentially just particle filter to estimate where the robot is. And then once we have the estimation of where the robot is comparing to the actual scan of the Kinect readings, then we could generate this path so to move the robot from the original place, which is somewhere here, and move it to the destination. So you can see the little green lines is the path that it generated, and also it has a obstacle. We implemented obstacle avoidance. So we'll jump into the simulation of G mapping so that you guys understand how how the actual mapping would look like. And let's see the video.
Okay, you should explain this. Explain what it's doing.
So this is a simulation that, remember that Brian mentioned that we have a gazebo simulator, and that's simulating how the robot is actually running in some indoor environment. And this is what we get from the localization algorithm, like the G mapping one. So this is the simulated environment.
And the right side was our base.
Mm-hmm. And this is the G mapping operating in the real environment. Let's check the videos.
Echoberry. 2103 Echoberry. And you can see on the right, that's the actual video recording of our robot. And on the left is Arvis showing the G mapping data. And you can also see we're using the RGB payload right here from the Kinect. And another thing to add is that the robot is being autonomously operated. So we're not giving it any keyboard commands. It's just doing everything on its own.
Oh, I kind of got stuck here.
Oh, yeah. Ah. Ah. Ah.
Why does it run by itself?
Okay.
Yeah, so it decided to interrupt itself, but that's what ended up looking like. So on the right, you can see the actual picture of the room, and on the left, you can see the grid mapping map that we created. And you can see here, there are these couple blotches that definitely look out of place, and that's because our Turtlebot platform wasn't able to fit into those areas and properly map out the features, basically. Next. And now, the debriefing slide. So what we've done in this project. So we initialized this Slammr platform. We deployed ROS and Ubuntu onto all our workstations and the master laptop. We established the connection between the laptop, the Kinect, and the iRobot Create using a USB interface. We established a stable network connection using a router. And we calibrated the Slammr platform using the gyroscope on the power board and the wheel encoders. We also implemented two different types of SLAM, and one of the SLAM, the grid mapping, was actually implemented in such a way it's autonomous. So we basically run it, and it runs automatically and will map out the whole room. And afterwards, we implemented waypoint navigation with AMCO localization. Next. So, where to next? One thing that frustrated us was we had to constantly recharge this robot. So one thing we think is very possible to do, just requires more time, is to implement the automatic docking of the iRobot Create into the charging bay. And another thing we could do with this without too much work is implement robotic telepresence or mobile Skyping that would allow you to basically talk to the robot. And if we had more time, we'd like to upgrade the Kinect to a laser rangefinder, which would give it better performance. And also upgrade the base of the iRobot Create into the Eugene Kabuki, which will allow us to recharge the laptop and I believe has some docking capability. I'm not too sure about that. But since we use platform-based design, we can take all of our code, all of our work, and take it to another platform, such as the Husky A200, which is a six-wheeled rugged vehicle that also supports ROS using a thin driver. Next. And we like to thank Jeff Jensen for mentoring us and helping us through these trials. And there's actually one more video. We actually want to show waypoint navigation in this room using a map we had built of Cori 204. But unfortunately, we can't run that because right now, looking at all the people and that extra table, the map is going to be completely different. And one thing that waypoint navigation does not do is update the map. It just can't do that. Just leave it alone, mate. So we're using waypoint navigation. That green arrow you just saw there was the goal point for the navigation. And you can see the turtlebot or the Slammr moving accordingly. And this is using the 2103 Etcheverry map. So what that 2D navigation goal dictates is the XY position and the yaw. Here you can see us setting another goal right there. And you can see it navigates around the central table right there without collision. And that concludes our presentation. Thank you.
Good job, everyone. Good job.
Any questions? Yeah.
So, like you mentioned that ROS has all these like really great open source tools and software,
Mm-hmm.
G mapping and Turbo and stuff.
Right, right.
And I'm just kind of curious, like, how hard was it to like use those with your project, and kind of like how much like tweaking and modification you have to do?
So the distribution. Oh yeah, Arvis.
Yeah, 'cause that's how
Okay, you know more about that than I do.
So basically, the tools are very useful because, like as you see, like all our data was outputted to this program, which they provide for us, which is Arvis. We didn't have to write any software to visualize our data. And what was your?
Like I'm just kind of working like,
Uh-huh.
like I'm just wondering if this stuff like works out of the box, or if it was like hard to use, or if you had to like modify.
Okay.
So officially, this platform isn't supported on the latest version of ROS that we use, ROS Forte. So we had to make some couple tweaks just to make it run. We couldn't follow all the online resources and tutorials verbatim because they applied to the previous version of ROS. And we found that that's where we invested a lot of time in getting this working.
And also for the G mapping algorithm that we have for the indoor localization, for the first one, the grid mapping one, it was fine tuned for laser scanner rather than for kinetic sensors. So it has some sampling rate issues, and also it has the accuracy issues. So there are some patterns that you really have to design to make it first navigate the room so that the scan data that it collects is sufficient enough to build up the map. Yeah, that's it. Yes. Yes.
So how is autonomous control? What determined autonomous control?
It was actually a pretty naive solution that because we didn't have time to implement anything more sophisticated, but it's basically it's a sort of like random walk, just because like it does not know the layout of the room ahead of time, so it'll just avoid obstacles and go through based on like a sort of random walk. At the same time, if we had more time, we would implement something where it would look at the map it's built so far and then attempt to flesh it out, travel to areas it has not seen. But we didn't have enough time to implement that part of it.
And if you're talking about the waypoint navigation, it's just an implementation of AMCL, and we didn't need to modify that too much for it to work. Any other questions? All right. Thank you.